I appreciate all these talks. I especially appreciate yesterday and getting into the nitty gritty of the geologic map units. But these talks today are like how you do everything, and so I'm really fascinated with this kind of the process. This is what we spend a lot of time thinking about, and so I appreciate this talking about mapping campaigns, talking about data interoperability, talking about nomenclature, both geographic and for samples, and how those things propagate together across geologic map units all the way down into the public domain and how we name things. And so all these talks are really important. And yeah, so this is just an extension of that. What we're talking about is trying to, and Brad talked about this a little bit, is the scales that we need to be worrying about and the kind of campaigning when we talk about map campaigning that we need to do. So next slide. Yeah, so I threw this slide up yesterday, kind of an eye chart, but just want to get back to it. And so we do have geologic maps of the moon. They've been published since the early 60s. Lots of the big people that we are trying to fill their shoes with and standing on their shoulders. And so all the way up to, right now. So Corey and his kind of unified geologic map at 1 to 5 million scale, this Krasnolnikov map that Jim Hebb was presenting yesterday, which is kind of the most localized map. And then this Chinese, from our Chinese colleagues that was published last year. So the main thing I want to point out here is that scales, okay? So I told you yesterday that I'd be harping on scales and content. And so this is another point. And so 3.8 million, 7.5 million, 1 million, 5 million, a whole bunch of 5 million scale maps, 5 million with the unified map from Corey, 2.5 million from the Chinese map that came out, and then 300,000 is the one that was most recently done. So we have kind of a discrepancy here, right? And this is not taking into account all the other maps, like I said yesterday, from Apollo, as well as morphologic maps, topical science maps. So we kind of have this scale issue. Next slide. And scale matters, right? And so here I have just an example going from the geologic map in North America, which itself is a compilation of a lot of different maps, all the way down to the geology of the SP crater kind of Cameron Quad north of Flagstaff, where we do a lot of this testing. And so on the left-hand side, the geologic map in North America, 1 to 5 million scale, just to kind of give you a hint of like this comparison, because we do 5 million scale mapping on the moon. This is what we're talking about when we put it on the Earth. And so in that little red box that outlines the state of Arizona, we have 19 units. In the entire map of North America, we have over 800 subaerial units. In this case, we also have submarine units mapped as well. So that shows you that scale discrepancy. In the middle, we have the geologic map of Arizona. Therein, there's over 49 units that are geologic that are mapped geologically. In the little box that is representing the San Francisco volcanic field, there are 4 units. And then if we expand on that on the panel on the right-hand side, the geologic map of the Cameron Quad at 1 to 100,000 scale. This is getting into more localized kind of mapping that we're capable of doing on the moon. We have greater than 25 units in this excerpt. Okay, so now we have a kind of a full range. You can see this. There's another, so that's a change in scale, a change in area, and you can see how the geologic maps are changing over that scale. Next slide. Another example is looking at some topographic maps. So this is an excerpt of actually map scale from the USGS. It's a little 2-page kind of reference document. These are not exactly the same areas, but it's kind of zooming out on Mount Rainier. And what you can see from left to right, on the left is 1 to 24,000. That's kind of 7.5 minute quadrangle scale. On the right-hand side is 1 to 250,000. In the middle is 1 to 100,000. So these are getting kind of around those scales that we're talking about locally for the moon. And so on the right-hand side, this kind of map is good for regional hazards, view sheds, kind of resource planning and some initial assessments. In the middle, this kind of scale is good for exploration sorties away from a base camp, applying those resource assessments, getting a better understanding about where everything is. And on the left-hand side, this is for traversing around kind of a base camp build out, resource extraction, and assessments. And so these are just examples of what different scales are going to provide for you. So in this case, is changing scale around the same kind of areas. Next slide. All right, so that's great. Scanner Aruba says, yeah, that's the way that goes. But we're talking about here is like, what kind of campaigning should we be able to do here? So when we started looking at this, there are different map kind of regions when we talk about quads for any body, including the moon. Brad was talking about before, these LAC charts. Those are quads that are kind of extracted out and try to compartmentalize the surface of the body at particular scales. So if we go to Mars, Mars Transverse Mercator, or the MTM quads, A lot of specs here, but it's basically transverse Mercator. These are these little lenses of a projection in 20 degrees of longitude, all the way from pole to pole. And so you have these little lenses, and they are increasing longitude towards the pole. They're the specs of them. They're all in transverse Mercator, except for the very poles themselves, greater than 82.5. They're done at 1 to 500,000 scale. So when we talk about 1 to 500,000 scale mapping using MTM quads, this is what we're talking about. And a lot of regions on Mars have been split down because of these kinds of sizes. It's positive west, and that results in about 2,000 quadrangles to split up on any one body if you split this up. So 2,000 MTM quads. Next slide. So this is the way it looks. And so this is Jezero Crater. This just gives you kind of a hint of how it looks. This MTM 2282, that's the quad kind of code. And that's a sea lat of 20 degrees north and a sea long of 282.5, which the 0.5 is truncated. So it's 2282. And again, that's in positive west. Each MTM in this case is about 300 by 300. Next slide. So if we apply this to the moon, so LTM, so this is Lunar Transverse Mercator, same kind of specs. The only thing is that because the body is about half the size of Mars, we have it at 1 to 250,000 scale. Also, something that we would change is positive eastward direction. We'd still go 0 to 360 just because the coding would matter for MTM or LTM quads, but it doesn't have anything to do with how the data is actually projecting itself. So this is what we propose. It's 1,964, so it's still 2,000 quads at LTM, so Lunar Transverse Mercator at 250,000 scale. Next. This is what the Lunar Transverse Mercator would look like for the Artemis 3 landing sites. And so just to give you an idea, on the left-hand side, this is Corey's unified geologic map that was compiled at 5 million scale. So that gives you a little bit of an idea about how these units look at these scales, as well as the topography on the right-hand side. Okay, these are the 13 candidate sites that we know right now. And one of the things that this really helps with is adapting those regional units into something that's a little more localized, so that we can, when we're operating at these very local scales, we have something that will bridge back into kind of these broader or more regional to hemispheric to global units. Next slide. Okay, so pros and cons. Pros, in my opinion, this LTM type of scheme would bridge regional to global to local. I think that that's really important. 1 to 250,000 is something that is comparable to what we've done in the past. We had 250,000 scale maps of the Apollo landing sites, and it bridges seamlessly. We talk about kind of these fifth scales. So if you're doing 1 to 1 million scale mapping on any body, you would be actually digitizing it at 1 to 250,000 scale or so. And so these kind of fifths or fourths that we have in scale is important, because if you do 1 to 1 million scale mapping, the next thing down is about 250 to 50 to 10 to 2. And so these kinds of fifths of factors are really important for us to be able to bridge information over. It's a familiar standard format to Mars, so we're all familiar with the way it looks. The shape, size, and linear scale, because this transverse Mercator is true for small areas, that is, it's conformable. It's a conformable projection system. The quads result in things that are of comparable size, and so that's good. It also enables targeted selection for exploration purposes. It mimics the 7.5 minute quads. Cons, it's important for us to note the cons so that we can identify the hidden dips and potential complications of any projection system and campaign that we use. So transverse Mercator is not computationally easy. There's a mitigation strategy for that. The number of potential ROIs is huge. So 2,000 is a lot, but targeting blocks of ROIs, regions of interest, is a way for us to mitigate that. And because it's not square in a digital environment these days, you know, we can transfer things that are not square into something that is square if that's a really meaningful thing for you. So in my opinion, small list of cons, a large list of pros. Next slide. So relevance, I'm going to skip over because I have one more slide, but this is a bridge scale that I think is really important. Next slide. Getting at the next step. So this is getting at what Brad was talking about before, about how we would do this. So exploration requires targeted, rapid turnaround maps. And one way that you can do this is to emulate the approach that's being employed right now for the analog activities to support Artemis lunar operations. This is what supports the JET-3 and the DRATS tests. It's in Rose's C23. This is short proposals that demonstrate PI capability, small competed teams working for a finite time, doing a collaborative mapping effort to select 250,000 and larger or smaller areas as needed, larger scale, smaller areas to support those needs. Targeted regions of interest that are high interest, and this can help satisfy exploration needs with community input. Getting that community input is really important. So this is just one more way that NASA could help with this. We're not here to direct NASA, but we certainly are here to talk about different ideas. And this is one way that we can do this without having to go through the proposal process where you have to have a scientific investigation. If NASA needs short turnaround maps, this is one way to do it. That's the last slide. Thanks.
Roger that. Thank you, Jim.